Welcome. This is going to be the second part of really process, probably the fourth part of moderation mediation. And so in this particular class, Class 8, we're going to talk about process moderation and mediated moderation or moderated mediation. I mean, you can view it a lot of different ways. So that's what we're going to be talking about. So again, you probably remember from last class our definition of moderation. Moderation is the combined effect of two variables on another. It's known conceptually as moderation, and in statistical terms as an interaction effect. And then here was our definition from Wiki. Again, I'm not going to read through this all again. I've read through it before. You can always, if you want to read through it again, you can stop the video and read through it. And if you remember, we went through a number of examples, but this would be the classic example of moderation. So again, the classic example of moderation would be general mental ability causes or leads to our GPA in college or high school, but that is moderated by demographic variables. So our general mental ability is not as valid for all different groups. Now, of course, that's a testable hypothesis. It might or might not be true, but that's what we're hypothesizing. Our moderator is then a demographic variable of some kind. Of course, we can have more complicated models. Here we have two types of moderation, and we have mediation. So here we have general mental ability leading to job knowledge, leading to job performance. But both of these paths are moderated by demographic variables. So the path from general mental ability to job knowledge is moderated by demographic variables. The path from job knowledge to job performance is moderated by demographic variables. Okay, at this point, we're going to return to Field. Now, if you remember, Field had an example of a moderate regression. At the time, we didn't look at it because Field analyzed it using process. And we weren't ready to look at process yet. But now we're ready to look at process, so we'll go back and look at his example of moderation. So Field had an example, do violent video games make people antisocial? Interesting question. His participants were 442 youths. His dependent variable outcome was aggression. His independent variable or predictor was number of hours spent playing video games per week. And the proposed moderator was callous unemotional traits. So callous unemotional traits. So that led to a model that looked like this. So again, here's our conceptual moderation model. We have a predictor, we have an outcome, and we have moderation or a moderator. We could think of this as being an X here. So in this case, if callous unemotional traits were a moderator, then we're saying that the strength or direction of the relationship between game playing and aggression is affected by callous unemotional traits. And so here's our statistical moderation model. Statistically, this is what it looks like. We have a predictor, we have a moderator, and then we have the predictor times the moderator. So again, if you remember back, we're going to have some predicted value, a y value for an individual, plus the constant b sub 0, plus b1 times a1, where a1 would be the predictor, plus b2 times b plus b, where b would be the moderator, plus b3 times a times b. So basically, again, aggression equals the constant plus b1 times gaming plus b2 times callous plus b3 times the interaction. So Hayes goes ahead and loads this into process. I'm not sure why Hayes's slide for this is so hard to read. He tends to do pretty good quality control. So, I mean, I took his slide directly, and you can see it's very hard to read. But we load in aggression as our outcome variable. Our independent variable is video games, and our moderator is those callous traits. You can see here our model is going to be number 1. So again, I said last class, you really have to be careful to put the right model in. If you put the wrong model in, everything's going to go wrong. So you have to put in the right model. In this case, the correct model is 1. He likes bias corrected bootstrapping. And then if we get over to here, you can see again, my process window for the process options looks different. So, but one of the options is mean center for products. So one of the nice things about one of the nice things about process, one of the nice things about process is you don't have to center the variables yourself. Process will actually create the centered variables itself. So process will create the centered variables itself. You do not have to create the centered variables. You can, but you don't have to. Process will create the centered variables. Also, you don't have to calculate an interaction effect. Process will calculate or produce the interaction effect itself. So two nice things about process. You don't have to center the variables. If you ask it to, it'll center the variables itself. You don't have to create an interaction. If you ask it to, it'll create the interaction automatically if it's a moderator. Okay. Also, another nice thing it'll be do is that if it's multi-categorical variable, it will automatically create the additional dummy variables. So it'll automatically create dummy variables. So that's a really nice thing about process. Makes it really handy. It does all this for you. You don't have to do this. Now, in the SPSS, the new automatic linear will do this as well, actually. But Field skipped on the new automatic linear, and so did I. I mean, you can always use it, but I think if you're using SPSS, you should go in and set up the regression yourself. But in process, it automatically will do the mean centering, and it'll automatically create your category, your dummy variables, and it will automatically create the interaction variable. So it does all that for you. That's really great, right? Isn't it? I guess that's why a lot of people use process. All right, so here's our first piece of output. So let me get my laser here. And you can see our y, or the outcome variable, the dependent variable is aggression. The x, or the independent variable, or the predictive variable is video games. And our moderator is that callous unemotional traits. It's a lot to say. Callous unemotional traits. Sample size 442. Outcome is aggression. Our model summary, our R for the total model is 0.6142, our R squared 0.3773. So our total model explains 37% of the variance in juvenile aggression or youth aggression. Our mean squared error, our F, degrees of freedom for that F, the P 0.0000, obviously it's significant. We look down here, we see this is our constant, our y-intercept. Again, it's significant. For the moderator, which is again callous unemotional traits, it is significant. You can see right here, 0.000. Here's its B coefficient, its standard error, its T, the bootstrapped confidence intervals for this B coefficient. And remember again, I told you last class, I hope you, if you didn't view last class, I'll try not to skip everything I said last time, just in case you didn't view last class. So one of the things about Hayes and process is Hayes does not really believe in the standardized coefficients. At least that's what I understand. He doesn't believe that much in beta, big B beta. He believes more in these B coefficients. So you'll see there's no standardized coefficient. And I believe you can get standardized coefficients for mediators, but I don't think you can get standardized coefficients for moderators, if I'm correct. But I could be incorrect, but I think that's correct. Well, but anyway, so this is our moderator. and it's the callous unemotional traits, it is significant. So our moderator is a significant predictor in and of itself. Then we have video games, viewing video games. Here's its B coefficient. It is significant. 0.0260 is the associated p-value. But of course, we're most interested in our interaction, since the interaction is what gives us moderation. So we say, is there moderation? Is there interaction? And the answer is yes. And the associated coefficient is 0.0271. The p-value is 0.002. And of course, here again are bootstrapped confidence intervals. And it's just showing us here that our interaction is equal to video games times CU, or times those callous unemotional traits. Okay, hope you understand that. I hope I went over everything I did last class with mediation. Again, the big thing is you'll see there's no betas in the process model. Although you can get them for mediation, I'm not sure if you can get them for moderation or not. Okay, then you can see the next thing it's going to give us is the conditional effect on x on y at values of the moderator. And it picks out basically the mean, right here, 0, and then plus or minus 1 standard deviation for the moderator. So it takes the moderator variable, and it's predicting the mean, and then one standard deviation below the mean, and 1 standard deviation below the mean. And it's giving you then the conditional effect of x and y at that point. I'm not sure you can interpret a lot from this just by looking at it. Again, I think you really have to go to the next step and also print it out. But if you go to field, he tells you how to interpret this in the book. Maybe it could help you interpret this directly. I, again, don't really think you can interpret this very directly without plotting it out or the next step. If we go to the next step, you can see it's just giving us conditional effect of x on y at a lot of different values of the moderator. And again, I'm not sure how helpful this is, and again, in a lot of cases, there may not be too many points at each of these values of the moderator. So I'm not totally sure how helpful this would be to you. I think, again, the most helpful thing is to move on. And to move on, one of the really nice things process will give you is it gives you the values. It gives you a syntax that you can actually copy and paste right into SPSS. So it gives you a syntax that you can copy and paste right into SPSS. So we can take this syntax right here and copy and paste it right into the SPSS syntax editor, and then just run it. So that's really nice. I mean, you could also, field says you can take these values and just cut and paste them into a data editor, a data window, and then you can choose which graphs to run on your own, which is true, but I'm not sure why you would do that. Like I said, you could just take, as long as you know how to copy and paste syntax in SPSS, you can just copy this syntax, paste it into SPSS, and run it. You can also, as another option, you could just copy these values, paste them into Excel, and then do your graphing in Excel. Okay, and what this is showing you, so basically this is different values of the video game, different values of CU, or callous unemotional traits, and then the associated aggression scores. Now, of course, I should note these are predicted scores. These aren't actual observed scores at these points. These are predicted scores at these points. So we can just load this into SPSS or load it into Excel and then run it. And if we do, we'd get something like this. So we see different levels of video game viewing, low, mean, and high. Different levels of these are the dependent variable, aggression. So this is aggression, mean predicted aggression. And again, it's the predicted scores, not the actual observed scores. And then we have different lines for different levels of callousness, or callous unemotional traits. So what we can see is that when callous unemotional traits are low, there's not much of a difference in terms of viewing video games. Viewing video games doesn't make much difference when callous unemotional traits are low. Increased viewing of video games doesn't even make much difference when callous unemotional traits are at the mean. However, when we take youth who are sort of callous to begin with and have them view video games, it does make a difference. Although we can see from this, just being callous, having callous unemotional traits makes a big difference in mean predicted aggression. At all three levels of video games, you have much higher aggression if you have high levels of callous unemotional traits. Okay? And again, you can see the biggest slope or the biggest increase is when callous unemotional traits are high. Watching video games makes the biggest difference, or the time spent watching video games makes the biggest difference when callous unemotional traits are high. And then Field gives you some advice on reporting this, so you can see what Field suggests to report. Again, we're reporting B values, the B value for the constant, B value for callous traits, and again, callous traits has been centered. Process automatically centers it. The B value for gaming, again, you can see the gaming is centered, as is callous traits. So again, process will, if you ask it to, you don't have to again, but if you ask it to, it will automatically center these continuous variables. It will center categorical variables as well if you ask it to. And then we have callous traits by gaming. So that's the interaction. You can see the B value there, and you can see he's giving you the standard error, the B and the T value, and the associated P value. When P is less than 0.000, Field's just reporting it as less than 0.001. But again, we have a significant interaction here, and we saw the nature of that significant interaction. The nature of the significant interaction is that when callousness is high, that's when viewing video games makes the biggest difference. And here's our R-squared 0.38. Okay, now we're going to go back and we're going to repeat our previous moderation analysis. So we've seen Field do a moderation analysis. Now we're going to repeat our previous moderation analysis. I'm coming to you to interrupt this TV show to just make a correction. So just so you have it correct as we go through these slides, I want you to know or remember that despite what I say, death pop is deaths per million. It's not per thousands or hundred thousands. It's actually deaths per million. So again, the error, the problem came about because the world site uses deaths per million for each state. On the other hand, most other people use deaths per 100,000, and also for most of the other variables, they used 100,000s or things per 100,000s. So I actually changed in the database the variable or created a new variable that was deaths per 100,000. But then a lot of times I still went back and used the death per million variable by my error. So all it does is put anything off by a factor of 10, really. It doesn't affect the interpretation of any of the analyses, but it does put things off by a factor of 10, and I apologize for that. But instead of changing all the slides, I'm just letting you know that whenever it says death pop, that's deaths per million, not per thousands or hundred thousands. And I thank you for your understanding with this issue. Our previous moderation analysis was with predicting COVID deaths in the population for each state, and the dependent variable, or the Y, was actually deaths per 100,000. We also had density, or density of the population per square mile, and average temperature in the state. And again, our sample size is 50. We have 50 states. And now this time, instead of running SPSS, we're running process. And you can go back and you can compare now these results from running process to the results from when we ran SPSS in the earlier class, if you would like. So we run it, and here's what the output's going to look like. I'm sorry if this is a little hard to see. This time I wanted to give it all to you. I didn't want to cut it off, but it does, I admit, make it a little harder to see. You might have to squint a little bit. So we can see our model summary. R, the overall R is 0.61. The R squared is 0.38. That means our model's explaining 38% of the variance in COVID deaths. Our mean square error, our F, 9.31. Degrees of freedom, associated degrees of freedom. You know, we have 3 degrees of freedom because we have 4 parameters. And then our p-value, 0.00. Then we have our model. You can see our constant, which is really just an interaction. Our density, which again, density here is our independent variable. And density has a coefficient of 0.78. It is significant at 0.00. And here's our bootstrap confidence intervals. We then have temperature. Temperature is also is not significant. So the P there is 0.38. So temperature itself does not affect COVID deaths. But the interaction, which the interaction is density times temperature, the interaction is significant. So as we saw before, there is a significant interaction. And here's the bootstrap confidence intervals. And here's the B coefficient for the interaction. Here's a test of the highest order unconditional interaction. In this case, there's only one interaction, so it's going to be the same thing as what we saw up here. And then here's our conditional effects of the focal predictor at values of the moderator. So again, this is similar. I should have said this on the previous slide. In ANOVA, this is similar to simple main effects. You know, so probably in ANOVA, you talk about simple main effects. This would be similar to simple main effects. Although, of course, we have continuous variables. So in this case, we have continuous variables, not categorical variables. But this would be similar to simple main effects. So here we have our conditional effects. Again, temperature 1 standard deviation below the mean, temperature 1 standard deviation above the mean. And it's just showing you the regressions or the effects at those points. Again, I think it's easiest once you actually go ahead and plot this. It's easiest to know what this means once you go ahead and plot this. So we're going to go ahead and plot it. Well, again, as did field, a process will actually give us this syntax that we can just load right into SPSS. So it gives us the syntax to load right into SPSS. These are the density values, the temperature values, and the predicted values for deaths per 100,000. Note, I could, if I wanted to, just go ahead and load these right into Excel as well. So there's 3 ways I could do this. I could just take the data, put it into Excel. I could just take the data, put it into the data editor of SPSS, or, which is the easiest, and which is what I did, I can just copy this syntax and just load the syntax into SPSS, and it will provide me with my graph or chart. So that's what I did. And it generates this graph. And so it's an interesting graph. You can see here's our different density values. And here's 3 different temperature values. And so you can see this is low density, high density. Again, the deaths per 100,000, the highest rate of deaths is when we have a combination of low temperatures. This blue dot, see this blue dot is low temperatures. When we have low temperatures and we have high density. When we have low temperatures and low density, our deaths are actually at the lowest. So this is sort of a classic interaction effect. If we draw our lines, which I'm probably bad at drawing, but so that's supposed to be a straight line. If we draw a straight line there and a straight line here and a straight line here, you can see we actually have that X effect. you can see, you know, in the old days of blackboards, this was even worse when I tried to draw lines. So I admit those aren't very straight lines. But anyway, so you can see when temperature is low, these are the three temperature is low values, what a huge slope this line has. I mean, this line is a big slope when temperature is low. So if you go back and look at the last slide, you'll see that. When temperature, so if you rewind and look at the last slide, you'll see that this slope is really big when temperature is low. And, you know, in a sense, the worst situation is to have low temperatures and high density. On the other hand, the slope is pretty much flat or even a little negative when temperature is high. When temperature is high, density doesn't make much of a difference. And then for temperature, the average values of temperature, it does go up. So for average values of temperature, it does go up, not as much as when it's low temperature, but there is an increase with density. And that's what we found before. If you remember, if you go back to our previous lecture, you'll see that that's what we found before. So this matches our previous lecture. So the graph makes it a lot easier to see. And now here I've actually put the lines in. So now I let SPSS draw the lines. So I let SPSS draw the lines, and you can see, you can see again this, that it forms an X. And you can see what these fitted regression lines here look like. So you can see the same effect. So I let SPSS add lines to the chart. And you can see SPSS draws much straighter than I do. And here again, you can see it. I believe this is our old one. This is the one I drew before with SPSS. You can see this is a little different. With process, this goes down. When I did it before, it goes up. That's because I don't, when I calculated the values for the for plus 1 standard deviation and minus 1 standard deviation, I did a little bit of rounding. So my numbers were a lot more approximate than processes are. So process has pretty exact values for 1 standard deviation above and 1 standard deviation below. Mine were rounded off a little, and so when I plot my chart, this line looks like it's going up a little bit. You can see in the process created charts, this line goes down a little bit. But other than that, it's highly similar. Okay, so if you compare this to the previous chart, you'll see it's very similar. And again, this chart was generated just using SPSS to do the moderated regression analysis. The last chart was generated from SPSS, but the moderated regression analysis had been run in process, and then we cut and paste the syntax into SPSS. Okay, another thing we can do here is to look at a moderated regression where we have a dummy variable or a categorical variable. Now I took a simple dichotomous variable. So we ran this regression before. Here we have, again, deaths, COVID deaths per 100,000, density, and this time region. If you remember, region was coded north-south. So we go ahead and run this. You can see our model summary again, R equals 0.60, which is pretty good for psychology studies, although this really isn't a psychology study. It's more of an infectious disease study. Our R square is 0.37, which would say that 37% of the variance in COVID deaths is explained by this model. Again, at the state level, not at the individual level. Our P is significant, 0.00. When we look at the model, our constant, significant, again, that doesn't matter a whole lot. These are our confidence, our bootstrapped generated confidence intervals for these parameters in the model or for these variables or factors in the model. So for the factor of density, you can see the coefficient here, standard error, T. It is significant. The p-value is 0.01. Region, again, that's north-south, is not significant. The interaction is significant. So again, we do get a significant interaction. Region interacts significantly with density in predicting COVID deaths. And again, region was coded north-south. So it's a categorical or dummy variable. So you can see the product term's key, the interaction is density times region. Okay, again, first we get the test of the highest order unconditional interaction. You can see that that's significant, but that's really just the interaction effect we already had. And this is pretty meaningless when we only have a two-way interaction, because we only have one two-way interaction. That's obviously the highest order unconditional interaction. So this is not going to give us very much information. We have the conditional effects of the focal predictor at values of the moderator. Note in this case, I let it go ahead and center a dummy-coded dichotomous variable, which I'm not sure, that to me doesn't really make sense. I said that before. I just went ahead and did it to see how it would come out. And so you can see when we do it, then it standardizes or centers those values. So we end up with the one region having a -1 standard deviation value of -0.66, and the other one having a +1 standard deviation value of 0.34. And then again, these would be the regression lines at that point, or not, at least the B effects at that point. Okay, so I'm skipping some steps here, but I've plotted the values now so we can interpret them more easily. And you can see, hopefully you can see it, that as the density increases, so do the number of deaths, but only for people who are living in the north. So as density increases, the number of deaths increase, but only for people living in the north. So this would be, these green values would be the north. The blue values are the south. So for people living in the south, as density increases, the number of COVID deaths actually goes down slightly, which is somewhat surprising, I guess. But so we're getting our clear moderator effect again. If I dare to try to draw a line again, which is pretty dangerous, it goes something like this and something like this. And so you can see again, it's a disorderly interaction, really. The two lines cross. Pretty much, again, for the south, it's a flat relationship. There's no relationship between population density and COVID deaths. But for the north, there's a pretty strong positive relationship between density and COVID deaths. All right? And if you go back, this should match up with what we did in our previous class when we did this ourselves using SPSS. If it doesn't, we're all in trouble. And let me know, because then I messed something up as we went along here. All right. At this point, it can really get complex, because at this point, we can start talking about much more involved or complex models. For example, we can have what's called mediated moderation. Let me try to say that again. Mediated moderation. And mediated moderation is when you have a moderating effect, and the moderating effect is then mediated. You can also have moderated mediation, which is when one or more paths in a mediation model are themselves moderated. So not only the models, but also the effects and variables within the models can then be named after their contributions. But this starts to get really complex. So you start to get into really complex models. And again, I'd suggest at this point, you turn to the process book, or Hayes's book, or Hayes's articles, and look at some of the different models that Hayes presents. I mean, Hayes presents an incredible number of already pre-programmed models. So this is just an example of, for example, Model 8. In Model 8, we have a mediation, but then we have two moderators of that mediation. So if you look at model 8 here, you can see X has a direct effect on Y. X has an indirect effect on Y through M, which is mediation. But then the effect of X on M is moderated by W, and the effect of X on Y is moderated by W. So let me repeat that. This direct effect of X on Y is moderated by W. The indirect effect of X on M is also moderated by W. And note, you could probably also have a situation where W moderates the effect of M on Y. So you can start to get really complex models. And this is model 8. Again, Hayes has a lot of models. I suggest you go to his Appendix A using process, and he'll show you a huge number of already existing models. If what you want to do doesn't fit into that model, you can always customize your model or create your own model. But Hayes does give you a lot of different models. But this just shows you that we can get into this really deep into the woods here, or really deep into the weeds, and we can start all these different models that mix moderation and mediation. I'm coming to you to interrupt this TV show to just make a correction. So just so you have it correct as we go through these slides, I want you to know or remember that despite what I say, death pop is deaths per million. It's not per thousands or 100,000s. It's actually deaths per million. So again, the error, the problem came about because the world site uses deaths per million for each state. On the other hand, most other people use deaths per 100,000, and also for most of the other variables, they used 100,000s or things per 100,000s. So I actually changed in the database the variable, or created a new variable that was deaths per 100,000. But then a lot of times I still went back and used the death per million variable by my error. So all it does is put anything off by a factor of 10, really. It doesn't affect the interpretation of any of the analyses, but it does put things off by a factor of 10, and I apologize for that. But instead of changing all the slides, I'm just letting you know that whenever it says death pop, that's deaths per million, not per thousands or 100,000s. And I thank you for your understanding with this issue. All right, so I wanted to do one Model 8 for you. I'm not going to go through and try to do all the interpretations of this, all the various graphs and plots of this, but I did want to at least take you through it, show you it's possible. So again, this would be a Model 8. We have one dependent variable, or outcome variable, or Y variable. In this case, it's COVID deaths. We have one independent variable, or X variable, density. We have one mediator variable, air pollution. And then we have one moderator, region. And again, region, because this is Model 8, region will be moderating the effect of density on air pollution, and also the effect of density on COVID deaths. So it'll be moderating those two relationships. And the outcome variable, the final outcome variable, again, is deaths in the population, or COVID deaths. So this is Model 8. If you want to go back, you can, the little model I just showed you what Model 8 looks like, and you can see what this, how this would then be set up. And again, we've already done analyses using both air pollution and found it to be a mediator, and region and found it to be an interaction. So here we go. Here's what our output would look like. First, of course, we start by predicting air pollution. And if you remember again, then we did say that the relationship between density and air pollution could be moderated by region. And you can see here it's not. I mean, you can see both density and region have an effect on air pollution. They have a main effect. They have a main effect. So density is significantly correlated with air pollution, and region is very highly significantly correlated with air pollution. And so they both have significant B coefficients. Again, these are B coefficients, standard errors, T's, p-values, and bootstrap confidence intervals, except we don't have an interaction. So there's no interaction between region and density in predicting air pollution. So that probably doesn't even really need to be in the model. You know, we could probably throw that out of the model, parsimony, simplify the model. Not that, you know, and I haven't said a lot about this as we went along because I hoped you knew it from the first semester or from, of course, our first 1 or 2 classes. But of course, when I talk in this class, I try to use language that's more understandable rather than strict statistical language. But of course, just because the p-value is not significant doesn't mean that effect could not exist. I mean, again, the fact that a p-value is significant, all it says is that how likely the data is given the null hypothesis. So a p-value just tells us the probability of that data occurring given the null hypothesis. We then have to make our own decisions. Of course, technically, a non-significant p does not mean an effect does not exist. It could just mean we don't have enough power, and probably always some type of effect exists. So, but, you know, even in journal articles and textbooks, if we went through that language every time, it would be hard to ever get anywhere. So we're saying there's no interaction effect. And then again, we only have one interaction effect, and this is the test of the highest order interaction, unconditional interaction. So the interaction effect is not significant. Then the next thing we're going to get is the prediction of the outcome variable, which is deaths in the population, or deaths per 100,000. We can see our model summary, our R is very high, 0.707. Our R squared is 0.50. Our P, it's significant, 0.000. Then we get our B values. Again, we don't get beta values. Process or Hayes isn't a big proponent of beta values. You can look online to see why that is. But we get our constant. We get our effect for density. You see, density now is actually itself not significant. So the effect of density is not significant. Air pollution is significant. Of course, in this case, we did not have a moderator between air pollution and deaths. Region is not significant. Region now becomes non-significant, but the interaction is significant. So this interaction between density and region is significant. And we really saw that earlier in this class, or earlier in this video or PowerPoint, that there is a pretty substantial interaction between region and density. And so here, region and density is significant. And again, the test of the X by M interaction, that would be the test of density by mediator, and that is not significant. So process will tell us, is there a significant interaction between the X value, which is density, and the M value, which is air pollution. And it's telling us it's not. There's no significant interaction. However, of course, again, there is a significant interaction between density and region. Okay, then it just gives us for the different values of region, our conditional direct effects of X on Y at our 2 region values. Now you can see this time I changed it up a little. I did not center the dummy variable or the categorical variable. So this time it's just using the 0 and 1 for region. Last time, if you remember, I allowed it to center those values. So last time I allowed it to center those values. And you can see, of course, that there's a large positive effect when for the north. So there's a large positive effect for the north. And then here's our indirect effects. These are indirect effects of density on air pollution, on death, on COVID deaths. And you can see it's going to calculate the indirect effects for each region. And that's because we told it that there was an interaction effect, a moderation effect. So it's going to give us the indirect effects for those two different regions. Okay, so what this is it's the indirect effects for the two different regions. And then it's going to give us what's called an index of moderated mediation, or a difference between conditional effects. In this conditional indirect effects, in this case, it's actually not significant. So it's telling us that the moderated mediation is not significant. I mean, the reason, again, we know it's not significant is because these confidence intervals include 0. So the moderated mediation, when we go through air pollution, was not significant. And, we saw that before. What is significant is the interaction between density and region itself impacting deaths. But the mediated relationship, or that indirect effect, there is not an interaction. And again, we only put the moderator variable on the A path. We could have put the moderator variable on the B path as well, but we only put it on the A path. At this point, I'm not going to get a lot more in depth in terms of trying to interpret or not interpret those effects. You can, of course, plot them. Actually, Process, I didn't show it to you, but Process did give me, again, the syntax, so I could plot the different interactions. In fact, though, and as I told you, I changed the air pollution data. This is the actual air pollution data. If you look at the actual air pollution data right here, you can see that air pollution is not significant. So this is the actual, I put in the actual air pollution data and ran the process model, just in case, you were really interested. And when we put in the actual air pollution data, the effect of air pollution as a mediator is not significant. And then the indirect effects are not significant. So the air pollution itself doesn't really have an effect. There is a moderation or an interaction between region and density. But the effects of air pollution, in all honesty, were not significant. But that wasn't very interesting. So I created some more interesting air pollution data for you. But again, in the real data set that I originally created, where I had the actual air pollution ratings, you can see there's no main effect, or there's no direct effect. This would be the B path. There's no path, that's the path between air pollution and deaths is not significant. So that's why I sort of made up some air pollution data. And at this point, what I just wanted to show you is that you can do other kinds of more complex models. So this was model 8, which is, again, a model where you have interactions between some moderator, and those interactions can affect any of the paths. In model 8, the interaction is on the C path, or actually you can look at it as a C prime path, but the path between the independent variable, which in this case is density, and the dependent variable, which in this case is deaths. And you can also, which we did have in this model 8, an interaction with the A path, which is the path between density and air pollution. We did not have an interaction with the B path, which would be between air pollution then and deaths. So I hope that makes some sense. Again, these are the types of things that would probably be a lot easier to do in a live class, where I could see if if you understand what's going on, if you could ask questions about what you don't understand, if I could see what I'm saying is just not catching on at all. But I hope you were still able to follow it. Certainly when we get to these mediated, moderated, or moderated, mediated, or even more complicated models, it gets really complex. I mean, again, the best advice I can give you is to start with that Appendix A of Hayes's process book if you want to use process. And again, as I also said, process right now, the official process is not available in R. There are some sort of unofficial knockoffs of process in R, but the official one is not yet available, except Hayes just did put out a beta version, and then I believe the official version should be out in a couple months. So if you want to try out the beta version, you can try it out. I find process runs pretty well in SPSS. Now, another thing, though, again, just like a warning to sort of end this lecture, is that the version field used of process was a little different than mine, quite different, for example, quite different than mine. For example, in that one analysis we discussed, he was able to put a moderator into the mediator slot. Now, I don't know if he could actually do that, if that actually worked. In my version of process for SPSS, a moderator has to go in the moderator slot, regardless of what model you're dealing with. So I don't know if what he did really worked in his version or not. Also, as I said, certainly a lot of the options he gave were different than the options I had. So I don't know if it's because he's using a different version of SPSS, a different version of process, or or a British version, or maybe it's a server version, because I think the server version could be a little different than the PC version. But I just wanted to warn you that you might have to play with it a little bit, because it could be that your version is going to be different than either Field's version or my version. But I will say process is rather easy to run and get the output from in SPSS. It's a nice addition to SPSS that you can run process through it. Okay, well, thanks for listening to me. It's probably a little cold for a Dairy Queen, but this is something from my youth, the old Dairy Queen, what they looked like in the old days. And I just thought I'd end with a happy thought with the Dairy Queen. We only have one more class left, and that's going to deal with logistic regression. So that's really a change in thought patterns to switch to logistic regression after all this process work. Okay, see you for the next class.